Samples from the moon's oceanus procellarum, an ancient mare basalt whose name translates to ocean of storms, may be able to calm at least one scientific squall, the source of lunar water. China's lunar lander Chang'e delivered the first real-time, on-site definitive confirmation of water signal in the basalt's rocks and soil via onboard spectral analysis in the year 2020. The finding was validated through laboratory analysis of samples the lander returned in the year 2021. Now the Chang'e team has determined where the water came from. The researchers published their results in the journal Nature Communications. For the first time in the world, the results of laboratory analysis of lunar return samples and spectral data from in situ lunar surface surveys were used jointly to examine the presence, form, and amount of water in lunar samples. The results accurately answered the question of the distribution characteristics and source of water in the Chang'e landing zone and provide a ground truth for the interpretation and estimation of water signals in remote sensing survey data. Chang'e did not observe lunar rivers or springs. Rather, the lander identified on average 30 hydroxyl parts per million in rocks and soil on the moon's surface. The molecules made of one oxygen and one hydrogen atom are the main ingredients of water, as well as the most common result of water molecules chemically reacting with other matter. The samples were collected during the hottest part of the moon's day at temperatures nearing 200 degrees Fahrenheit when the surface would be at its driest. The timing also coincides with low solar winds, which can contribute to hydration at high enough power. Even with such dehydrated conditions, the hydration signal still appeared. So the researchers asked where did they come from. First detected by the lander's onboard lunar mineralogical spectrometer in 11 rock and soil samples and further confirmed by 5 additional multi-part laboratory analyses on 8 of the samples, the hydroxyl was found to originate from 2 different sources. A small portion appeared in glassy material made by solar winds interfering with the lunar surface, just as it did in an Apollo 11 sample collected in 1971 and tested in the early 2000s. But the Chang'e sample only contained about a third the amount of solar wind generated hydroxyl containing glass as the Apollo sample. This suggests that the solar wind still contributed, although weakly, to the hydroxyl contents observed in the Chang'e landing site. The bulk of the hydroxyl in the Chang'e samples was contained in apatite, a crystalline phosphate-rich mineral naturally found to be on the moon as well as Earth. This excess hydroxyl is indigenous, demonstrating the presence of lunar-originated internal water in the Chang'e lunar samples. And that water played an important role in the formation and crystallization of the late lunar basaltic magma, the researchers said, referring to the composition of Chang'e landing site in the mare basalt of oceanus procellarum. By investigating lunar water and its source, the researchers are learning more about the formation and the evolution of not just the moon itself, but also the solar system. In addition, lunar water is expected to provide support for future human lunar in situ resources. The researchers are planning subsequent lunar explorations with Chang'e successors, Chang'e 6 and Chang'e 7. They will continue researching lunar water via remote sensing, on-site detection, and laboratory analysis to better understand the source, distribution, and temporal variation of lunar water, including polar ice.